So our next thing, it's reaction and nitration of our ring. So if you start out with a nitro group, we've seen this before, you can reduce nitro groups to amino groups using iron and acid. And the reason for this is if you want an amino group, there's not a very easy way to add amino groups onto rings. And so you can do a reduction reaction, so you can reduce it to the amino group using iron or zinc as the reducing agent. And we'll talk about this later, that if you want an amino group, there's a reason why you might want that on the ring, and there's a reason why we might want a nitro group, and it's very easy to go backwards. We can actually do an oxidation to make this ring go backwards. We do add a base at the end because the amino is a base itself and will pick up extra acid, so you add a base to prevent that. Lastly is acylation. If you want to take an amino group on the ring and make it into an acyl group, we've already seen that in Unit 1, and we'll talk about why these might be important later on. So why are these changes important?
Amino into amides, and remember, amides are not as good of an electron donating group as an amino group is. If the amino is attached, the nitrogen is attached to the ring, they're also bulkier. Nitro groups are electron withdrawing groups, amino groups are electron donating groups. So we can actually play around with the substituents and change their behavior. And it's these substituents and switching them up to different things that we can influence how a reaction is going to behave. So generically, when we see substituents being written anywhere onto the ring, we don't know where, we use the aromatic ring with the circle to represent full conjugation through the ring, and an X through that, a line coming out of that with an X to represent that substituent. And so whenever we are drawing these, if we don't have a specific position, that's what that's going to look like. So the first reason in terms of why they're important is has to do with the electronics of that substituent. So electron withdrawing groups, recall from when we talked about them previously, those are things like nitro groups, halides, ammonium groups, carbonyls. We can play around with the electronics of this reaction by utilizing the fact that electron withdrawing groups pull electron density from the aromatic ring. When I teach medicinal chemistry, we do have this as an option for looking at the behavior of medicines, for instance. We call this change theta, and there's an equation that relates that. This is a Hammett coefficient. And you can look at the Hammett coefficient, and theta is drawn on the screen, to look at how these molecules behave in the body with different biochemical molecules like enzymes and DNA. And it's with these chemicals in your body that you can look at how well it's going to do whatever reaction it's going to do. Now, recall electron donating groups are going to donate electron density, so they'll donate electron density to the aromatic ring. And also remember that aromatic rings are the nucleophiles in electrophilic aromatic substitutions. So the aromatic ring being the nucleophile, it's the HOMO of the aromatic ring that's going to react with the LUMO of the electrophile. So by adding electron donating groups and withdrawing groups, you're going to influence the rate of the reaction, because electron donating groups increase the energy of the HOMO, meaning that the energy is going to rise and then be closer to the LUMO of the electrophile. Opposite is the electron withdrawing groups are going to lower the energy of the HOMO, making the distance, the energy gap, the energy difference between the HOMO of the nucleophile and the LUMO of the electrophile being so far away from each other. It's going to be harder to do the reaction. So there's going to be a larger energy difference, and so it's harder to react. On the other hand, with the electron donating groups, because you have a smaller energy gap, it's easier to react. You're going to have a smaller energy difference between the HOMO of the nucleophile, which is the aromatic ring, and the LUMO of the electrophile. So this isn't any different than any of the other reactions that we've talked about before. So we can then look at the substituents themselves. So if you look at this example, I have benzene having a relative rate of 1, meaning that that's our standard, where it's just hydrogen. And when you compare it to the phenol being a strong electron donating group by resonance, you see that it's 1,000 times faster. And so the electron donating group will activate the ring and make the ring more reactive. And halogens, on the other hand, on the other side, they're mild electron withdrawing groups by induction. And so they're going to slow down the reaction, but not as much as the nitro group, which is an electron withdrawing group by resonance. And because we have this electron withdrawing group by resonance, it's going to be an even stronger electron withdrawing group, and therefore it's going to be an even slower reaction. This is not to say that the reactions don't happen, they're just going to be very slow because you have these mild reactions happening. So again, one more time, is that these substituents are already on the ring. If you're trying to add additional substituents onto the ring, we're looking at the behavior once these substituents are already on the ring. So if I wanted to add another group onto the ring, how fast is this going to behave? So here is another kind of reminder of these things. So the electron with donating groups, the alkyl group is donating by hyperconjugation, and then we can have electron withdrawing groups, and so our electron donating groups are going to activate the ring. Activate means that it's going to make it more nucleophilic. Electron withdrawing groups deactivate ring, meaning it's less nucleophilic, so the ring is going to be less reactive towards whatever electrophile that you have. And the electron donating groups are going to be more reactive to whatever electrophile that you have. And so the next thing is, how do the substituents affect the molecule in terms of where do the next stuff go? And so wherever we have our substituents on the ring and we add the electrophile, there's a couple of different possibilities of things where things go. So let's say we have this molecule and we have some sort of substituent on there, and then we add the electrophile. It can either go next door, so 1, 2, which is ortho, or I can go 1, 3, which is meta, or I can go 1, 4, which is para. So recall that when we were looking at previous reactions, we didn't already have substituents, and so here we're going to have our substituents, and it's going to be based on resonance. So certain types of electron withdrawing groups or donating groups are going to affect.
If we look at the data for adding things, so for example, adding nitro groups, depending on the substituent, we see variations on where things will go. So we see that when we have the electron donators, that we get certain sets. So in this case, I highlighted some electron withdrawing groups, and you can see as they get stronger and stronger, we have a preference for the meta. So the first one, the first two are really strong electron donators, electron withdrawers, so they're going to have a preference. You're not only going to get the meta, but you'll get more meta. And so you can see that there's different ratios. So if I were to ask you, which one would you get the most from, you would see that, and you can also justify the ratios between how much ortho and para. So you have definitely more ortho position, but para is more available. So with electron donating, you see you get more of the ortho and the para, but as your substituent gets larger and larger, you notice that you start getting more para. So for example, the C-tantalide, which is the last thing that's on the list, when you add a nitro group, you get more 79%, and that's why we see that. Now for the halogens, we see halogens are the weird ones. Halogens are kind of in between. They're both electron withdrawing groups, but because they have lone pairs by resonance, they're going to act as orthopara. So they withdraw density from the ring, they deactivate the ring, and they deactivate by induction, but they're going to be donators by resonance. So they act kind of in between. And so that's a key thing for you to remember.
So let's talk about kind of just a quick overview on why things go this way. There are two ways that we can draw the resonances. One is involving what we call the secondary resonances, which is what we're going to do today. And then what you're going to do in your classwork is going to be the resonances once we've already added the molecules. So there's two ways of explaining. They both actually support each other. And so if I draw my resonance structure, putting my electron donating group into the ring, by putting the electron donating group into the ring, I can see that I have a negative charge that we have placed on the ortho position in that first resonance that I have drawn. And then I can rotate that negative charge through the ring, and once we've drawn all the resonances, we'll see that there's a negative charge placed in the ortho and the para positions. And like I mentioned, that we can draw these resonances with the secondary resonances. Secondary resonances means that I have some substituent of the ring that facilitates showing us how this reactant is going to behave in a mixture. The resonances that you'll draw in class are what happens after you already add, and it helps to support this. So you're going to draw sigma complexes and draw their resonance. So what this tells me is that the ortho and the para positions are strongly nucleophilic or more nucleophilic than the meta positions are based on my resonances, because they have a negative charge at those positions. And so the electron donating group by resonance is going to support making those positions more reactive. Now, if I take electron withdrawing groups by resonance, so for instance, amino groups, nitro groups, carbonyls, and I draw the resonances, the pi bond in the ring puts electron density towards the carbonyl. And by doing that, the first resonance that I'm going to draw, you'll see has a plus charge on the ortho position. And then I can rotate that plus charge through the ring by resonance. And when I rotate them, they're going to end up in the ortho and para positions. So we end up moving our plus charge into the ortho and para positions. This then tells us that the ortho and para positions of this molecule are less nucleophilic. Remember, we're using these molecules as a nucleophile, so our argument is going to become towards the nucleophilicity of these molecules. So they become less nucleophilic at those positions. And because they're less nucleophilic at those positions, the only possibility left on my molecule is the meta position. So in terms of directing effects, my electron donating group makes the ortho and para positions more nucleophilic, and my electron withdrawing groups makes the ortho and para positions less nucleophilic, and therefore we see the directing effects of electron donating groups going to ortho para, and electron withdrawing groups facilitating things not going into ortho and the para position.
All right, so in addition to talking about what spots on an aromatic molecule will be more negative or more positive depending on what's on there, so kind of quick little overview. So when we have, in terms of resonance, when we have electron donating groups, we see that in the ortho and the para position for the resonance, they're more negative. So that means if it's more negative, that means these are the more nucleophilic spots, and the more nucleophilic spots mean that your electrophile can be attacked better on those sides, which just means that we're going to have a preference for the ortho and para, and you saw that in the little clip before this. When we're talking about electron withdrawing groups, remember, they make the ring a little bit more positive, and it turns out they're a little bit more positive at the ortho and the para positions, which means that these positions are less nucleophilic, since we're talking about the ring being a nucleophile. So I know we're saying positive, but that, because the ring is a nucleophile, we're saying it's less nucleophilic, so what's left is meta. So you have a little bit more meta. So there's less positions that are available, but those are going to be the positions that are a little bit more nucleophilic. And not more nucleophilic because of resonance, making them more nucleophilic. It's just that they're not as positive. So the other way to look at this is from the arrhenium complexes. So there's two ways that we need to look at it, and you should be comfortable and okay with looking at both. So if I take an electron donating group and I were to add something to the ring, so let's go ahead and add a methoxy as my electron donator, and I wanted to do an electrophilic addition, and let's say we use the para position. So that's our strong electrophile.